So here, let's start. To get started, the damped rotational system has been created for you. It has been created for you. So this, which we know how to make it. We already done it with it. We already done with it. Set the following values on the block. Rotational damper with a damping coefficient of 10 Newton meter per radian second. 10 Newton meter per radian second. Inertia of 1915. Inertia is 1915 kilogram meter square. 1915 kilogram meter square. And PS constant, torque of 50 Newton meter. A torque of 50 Newton meter. Okay, this is task 1, as easy as that. Task 2, they are telling you the generators operate more efficiently when running at high rotation rates, right? So you know about that. All generators operate more efficiently when running at high rotation rates. But the water wheel spins at relatively low speed. So the water wheel spins at relatively low speed. To increase the efficiency of the generator, you can add gearbox. Okay, so here they ask you in this task actually to add a gearbox then. Okay. So we add a gearbox and we should add another output inertia. Connect the inertia to the input port of the gearbox. Good. All right. And here they don't ask to have the other inertia, just the output, just the input, and they ask you change the gear ratio to 0.01. 0.01 gear ratio. So with that gear ratio, you are speeding up the output. Okay. Let's see in the next phase. Okay. So in this phase, here what we did is just we are speeding up the output. The rotational electric, so now we don't need to add another inertia and mass, maybe because here you don't have mechanical system at the output. Here just you take that value of velocity, which is now like increased by how much? Increased by 100. So if your velocity here, let's say small, whatever it is, you time it by 100 and you get it from here. The rotational electromechanical converter block is available in the electrical element. So I can find it if I need it. They will ask about it in this blue task. This block relates torque and angular velocity to current and voltage via a constant of proportionality. Okay. So it's clear that this block relates the current to the torque and the angular velocity to the voltage by this formula. So that you can convert from mechanical domain to electrical domain. Okay. In the mechanical domain, you have the torque and the angular velocity. In the mechanical domain, you'll be having the current and the voltage. Also, you can relate electrical to mechanical. So you can design generator or a DC motor, right? If driven by an electrical source, so this can represent an idealized DC motor, right? If driven by a torque or angular velocity, okay, So this can represent a generator. Your task now is to add the rotational electromechanical converter. Electromechanical converter. Okay. Here is the system. Okay. To keep the model organized, you can flip the block left right using either Control L. So if I use Control L, this block should be okay. It opens for me the library actually, which is not what I want. Okay, or format tab of the Similink, etc. So I can say right click, I think, and format, and saying flip block. Good. So the reason why I'm saying that, so then I can have the green here. Green is for mechanical, clearly speaking, and then it will convert it, the mechanical energy to electrical energy. And so that a generator, as I said. Connect the R port of the converter to the O port of the gearbox, which is expected, right? Set the constant of proportionality to 0.2 volt per radian per second. Zero point 0.2. All right, that's it. Let's see, task 4. Now, the rotation of the water wheel is coupled to the rotation of the generator. Like other rotational elements, the rotational electromechanical converter has R and C ports. Like any rotational element, has R and C. Okay. And both needs to be connected to your physical network. And here you will designate the C port to the rotational electromechanical converter as fixed to represent the stationary generator body. So you connect C to the reference frame. Okay. Which is here, okay? We can have it here, it's the same. Good. Add a second mechanical rotational reference to the model. Well, you can add another one connected to the C. Anyway, so I will keep the one which we have. I don't want to add one. Is all right. So on this task, the generator needs to provide power to a load. Okay. For example, a battery. In this exercise, you will use a resistor to represent a generic load. Let's use a resistance. Okay, resistor. All right. So I can use Control R, I think, and I connect the positive to the positive. All right. And the negative, I should connect it to the ground. So electrical reference. Good. And they are saying us to take a resistance of 100. That's your charge, that's your load consumption. And here you are measuring at the output, you are measuring omega. And omega, what is omega here in this case? Well, apparently omega should be the angular velocity, maybe here or there. Okay. Yeah, but that's what they asked. That's what they ask for at least, but I think the graph represent, here the thing is the visualization, they don't tell you to visualize it yourself. But we know how to visualize anything, okay? So we connect it to the scope at the end, right? All right, so you are visualizing here the angular velocity, okay, of the energy. Further practice for you, the batteries, if you want to charge a battery, for example, are modeled using the following equivalent circuit, R and C. Replace the resistance in your model with this equivalent circuit. Use a voltage sensor across the circuit to see how a battery charges in the system. Good. Okay, so now we will go over the fluidic circuit.